for this equation, we're trying to solve it between 0 and 360 degrees. So that tells us we want solutions in degrees. That means if we're using our inverse trig functions on a calculator, you want to make sure your calculator is in degree mode. And then if we look at this equation, this is quadratic in form because we've got a cosine squared. Now this one, there are actually two different ways we could go about solving this. One is to get everything on the same side so that we've got a 0 on the other side. We could do that by subtracting 9 from each side. And then we could factor this. Since everything here is a square and it's subtracted, we could factor this as the difference of squares. That would be 5 cosine x plus 3 times 5 cosine x minus 3. Then we would take each factor and set it equal to 0. And solve for cosine of x in each one. This one, if we solve for cosine of x, we would get negative 3/5. This one, if we solve for cosine of x, we would get positive 3/5. So that would be one way to get these two solutions. Another way, since we've just got the squared terms on each side, we could take the square root of each side. When we do that, on this side with the number, we have to do plus or minus so that we get the two different solutions. So on this side we'd have 5 cosine of x. On this side we'd have plus or minus 3. And then we could divide the 5 on both sides, so we'd get cosine of x equals either plus or minus 3/5. So we get the same two solutions either way. From there, we want to use the inverse cosine. And since we've got the positive and negative of the same number, 3/5, then what we can do is find the first quadrant angle that would have a cosine of 3/5, and what we're going to want is all the other quadrants that would have either positive or negative 3/5 for the cosine. What we're going to do is solve this one first, just for the first quadrant angle. That means we're going to do inverse cosine of 3/5 on our calculator, and again we want to make sure this is in degree mode. That's going to give us 53.1 degrees approximately. And this said round to 1 decimal place. So that's our solution rounded to 1 decimal place. This is our first quadrant answer, and it's also our reference angle. So for our second quadrant angle, we're going to take 180 degrees minus this, which gives us 126.9 degrees. For the third quadrant, we're going to take 180 degrees plus our reference angle, and that gives us 233.1 degrees. For the fourth quadrant, we would take 360 degrees minus the 53.1, and that gives us 306.9 degrees. This gives us the solutions in all 4 quadrants. So first quadrant, second quadrant, third quadrant, and fourth quadrant. Then for part B, where we want all solutions, we would take each one of these and add 360 degrees times n to get all of our coterminal angles. We'd have the 53.1 plus 360 degrees n, the 126.9 degrees plus the 360 degrees times n, the 233.1 plus the 360 times n, and the 306.9 plus the 360 times n. And for this equation, we're solving it over the interval from 0 to 2 pi. That means we're working in radians this time. So you want to change your calculator to radian mode. And this is also an equation that's quadratic in form. This one we already have a 0 on one side. What we want to try to do with this is factor it, so we want to think of it as a trinomial. If you want to put an x in place of the sine of theta, that might make it easier to think about how to factor it. So instead of sine squared, you can make that x squared, and make that x, and make that a minus 2. Then we're doing trinomial factoring, so we have an x and an x. We want two numbers that multiply to 2 and subtract to 1, so that would be 2 and 1. Now let's go back and replace the x's with sine of theta. And we're going to take each factor and set it equal to 0. And then solve each one of these for the sine of theta. For this one we get the sine of theta equals 2. This one we get the sine of theta equals -1. Now we're ready to use our inverse trig functions. For this one, this is actually not possible. This is outside of the range of sine of theta. Sine theta can only be between -1 and +1. So for this one, there's actually no solution. For this one, we're only going to find one solution between 0 and 2 pi. Sine of theta is only equal to -1 at 3 pi over 2. We only got one solution for part A. Then for part B, we're trying to find all solutions, so we just want all the angles coterminal with this one. That's going to be 3 pi over 2 plus 2 pi times n. One more example for these. This one we're solving from 0 to 2 pi, so this is in radians again. And this time we've got two different trig functions in our equation. But if we get everything on one side and try to factor it, this isn't going to factor. This is one where we have to think of something else. Another possibility to look at is trying to square both sides, especially because we know we've got an identity that involves tangent squared and secant squared. So if we could get those two in the same equation, then maybe we could use that identity to simplify it somewhat. When we square both sides, on this side we have to square the entire side. We can't square each part separately. So it's this entire quantity squared, which means we have to write it out twice and FOIL it. If we do that, we're going to get tangent squared x plus 2 times the square root of 3 tangent x plus the square root of 3 squared, which is just 3. And over here we get secant squared. We still have our two different trig functions. Here's where we want to look for an identity that we could use to make this simpler. One thing that we know is that secant squared x is the same as tangent squared x plus 1. So if we replace this with tangent squared x plus 1, then we would have all tangent in this equation. We'd be down to just one trig function instead of two. Let's try that. We're going to replace this with tangent squared x plus 1. Now what that did for us is that now we've got a tangent squared x on each side. If we subtract it from each side, then those are both going to just cancel off. Then with what we have left, this is actually now a linear form equation because we just have the one trig function and it's not squared. We want to solve this for the tangent of x. We're going to subtract 3 from each side. And then we can divide both sides by 2 times the square root of 3. That gives us tangent of x equals -1 over the square root of 3. Now this is one of our special angle values. Tangent is sine over cosine, so this would happen where sine is 1/2 and cosine is the square root of 3 over 2. Only one or the other of them has to be negative. We could figure out the reference angle for this in the first quadrant. In radians, that would be pi over 6, because that has a sine of 1/2 and a cosine of the square root of 3 over 2. Now, if we're looking for solutions between 0 and 2 pi, we want the quadrants where tangent is negative. And that would be quadrant 2 and quadrant 4. Here's our reference angle, so we want the angle that goes with that in quadrant 2. We just want the one that's in the same family that's in quadrant 2, where we could think about taking pi minus our reference angle. pi minus pi over 6 would give us 5 pi over 6. In quadrant 4, we would be taking 2 pi minus pi over 6, and that would give us 11 pi over 6. These are our two solutions in the interval from 0 to 2 pi. Then for part B, we want to find all solutions. We're looking at doing coterminal angles with these two, but on this one again, since we're talking about tangent, these are actually pi units apart, so really we only have to write down the first one and then just do multiples of pi. We have 5 pi over 6 plus pi times n. That would cover the 11 pi over 6 and any other angles coterminal to either one of those two.